So in this example, we're going to use the Lagrange remainder to figure out how far out we have to go in a Taylor polynomial to get a desired degree of accuracy. So we might have a situation, right, where we need to approximate a number to within 1/100th or 1/1,000,000th, and then we have to know, well, it's helpful to know beforehand how far out you have to go in the Taylor polynomial. Do you need to go to the x to the 5th term, x to the 6th, x to the 200th, right? How far do you have to go? So just a quick reminder, here's the Lagrange remainder, courtesy of the Lagrange remainder theorem. So this is for some c that's between 0 and x. So the error in a Taylor polynomial approximation can be expressed as the next derivative evaluated at some unknown point c, and then times x to the n plus 1 over n plus 1 factorial. And now our goal in this example is to figure out the degree of the Taylor polynomial that we need if we want to approximate, say, e squared to 3 decimal places of accuracy. So accurate to within, say, 0.0001. Just as a reminder, this is the Taylor polynomial for e to the x. It's 1 plus x squared over 2 factorial, x cubed over 3 factorial, all the way out to x to the n over n factorial. So we have a little bit of work to do to turn the Lagrange remainder from this form into something we can actually compute with. So let's do this in a couple of steps. First, we know the error at 2 for n is going to be the n plus first derivative of f evaluated at some point c. But remember, the function here is e to the x. And so this is kind of like the nicest possible situation for derivatives, right? The derivative of e to the x is just itself. So is the second derivative. And the third derivative, all the way out to the n plus first derivative. So this piece just looks like e to the c. And now I'm multiplying by 2 to the n plus 1 all over n plus 1 factorial. Now that e to the c is a little tricky because we don't know what c is, so we can't do any calculating yet. But what we do know is that c is less than x, for example, because my x is positive and c is between 0 and x. So I'm going to have second step, we'll use absolute values here. If this is less than or equal to e squared 2 to the n plus 1 over n plus 1 factorial. But that's still not quite good enough because the e squared, that's the thing we're supposed to approximate to begin with, so we don't want it to appear in this expression either. So we want to get a decent but an upper bound for e squared. And we use the fact that e, which is about 2.718, that's less than 3. So our third step is to get a bound on that e squared. So this is the same, or not the same, but it's less than or equal to 3 squared 2 to the n plus 1 over n plus 1 factorial. That's 9 times 2 to the n plus 1 over n plus 1 factorial. So now we finally have something we can calculate with. And the rest of this is really trial and error with capital N until you find one that's big enough to make the error be less than 0.0001. So experiment N. So the error involved, 9 times 2 to the n plus 1 over n plus 1 factorial is less than 0.0001. And I think if you use your calculators to do this, The magic number will be n is equal to 10. So let me check. If I used n equal to 9, then I'm going to get 9 times 2 to the 10th divided by 10 factorial. And that's about 0.0025, so n equals 9 isn't quite high enough. But n equals 10, 9 times 2 to the 11th divided by 11 factorial, that gives me 0.0004, so not quite. Let me try one more. If n is 11, then I would take 9 times 2 to the 12th divided by 12 factorial, and that does it. I get 0.00007. So n equal to 11. All right, so the result of all of this work is that we could know before even doing the approximation that if we want at least 3 decimal places of accuracy in an approximation to e squared, we would have to use a Taylor polynomial that goes out to at least the x to the 11 over 11 factorial term.